All right, we start a brave new world. So we're done with our series inner sequences. Now we're going to omit one section of here and start with the good stuff. The good stuff that we're going to talk about for the rest of our section and for kind of most of the rest of this chapter is parametric equations, the calculus of parametric equations, polar coordinates, and then the calculus of polar coordinates. After that, we'll only have one more section on numerical integration. That's our course in Calculus 2. So we are on very much the downhill slope. So we start something new in plane curves and parametric equations because sometimes it's really hard or impossible to define a function or a curve as a function. And so we have a different way to do that. So like I just said, I'm going to be writing a lot. I'm going to write a lot of notes on the board because this is probably brand new to all of you unless you had the class before. So first thing I had to do is define what a plane curve is. Plane, not the thing that goes and curves around. That's not the type of plane curve we're talking about, okay? Talking about a curve on an actual plane. So not a three-dimensional curve, a two-dimensional curve, just somewhere on a flat surface. Does that make sense to you? A three-dimensional curve would be like a curve in 3 space. That would be in your next semester calculus. So here, what a plane curve means, it's just the motion of an object on a plane. That's really all it is. So when you see this word plane curve, what's that mean? Well, what this is simply the motion of an object in a plane. Now, I'm going to list out for you, I'm actually going to write these out so you have some good notes here. There's a problem with always defining a plane curve in terms of x and y, rectangular coordinates. So there's a few problems with this. So problems with defining a plane curve. So the motion of an object in a plane, that's what we're talking about here. Like a normal function. And what I mean by that is like a function in terms of x and y. That's typically what we do, right? We look at a curve and we say, okay, this curve, it's on an xy coordinate system. It's on a plane. And for any plane, we should be able to go, okay, here's your y, here's your x. We should be able to define the motion of that curve with x's and y's, correct? It's at this point, then it's at this point, and if it's on a plane, it should always be on the xy coordinate system. So why is there some problems on defining a plane curve like a normal function with x's and y's? Well, we're still going to have x's and y's, but the way we describe them, sometimes we have a problem because those curves, they're not always functions. So one problem we run into with plane curves is that many times, so here's the problems to define a plane curve like a normal function. Problem number one, a lot of times they're not functions. Many times they are not functions. Well, if something's not a function, it's really hard to describe it as a function. You can't say the function of y in terms of x because it's not a function. That's an issue. There's a couple other problems. Second one, a lot of times these curves, even if they are functions or if they're not functions, they can't be explicitly defined in terms of one variable. Like think of a circle. Is a circle a function? No. And the equation for a circle is x squared plus y squared equals r squared, isn't it? Can you describe that in terms of one variable? Well, you can. You can take a square root with a plus or minus, but you can't explicitly do that and still have a function. You can describe it, and it will make that circle with the plus and minus, but it's really hard to do that. It's awkward. Some of them you can't do at all. So that one you can define explicitly. It won't make a function, though, so don't go into that misconception. Some of them you can't even do it. So the second problem we run into is, well, firstly, some of them aren't functions. A lot of them aren't functions. Nextly, even if they are, or if they're not, a lot of them cannot be explicitly defined in one variable. So many we cannot explicitly define in terms of a single variable. And there's another problem. You see, with a plane curve, if a plane curve is more than just a curve of points, if a plane curve defines where an object is, does it make sense to you? A plane curve is the motion of an object in a plane. It's more than just a set of points. A plane curve has a connotation that this little bug starts here, or this whatever starts here, and this bug travels. So this bug has a starting point. It has an ending point. So imagine like a fly on the board. The fly goes, and then I hit it. But if I miss it, it's going to walk a little bit, right? Because I don't like flies. I really hate mosquitoes. So if you see me just, I'm not going crazy. It's a mosquito. So this bug lands on the board. The board is a plane. This bug goes, is this bug going to make a function for us? Probably not, because it doesn't necessarily respect mathematics, this darn bug. It might not make a function for us. Could you describe the motion of this curve with x's and y's? Yes, you say here, here, here. But if you try to do it with only a normal function, it'd be really hard to do. Firstly, it's not a function. Secondly, if it's just a listing of all the points, it's not giving you when this bug was at a certain point. It's also not giving you the direction that it traveled. So if I just list out this, do you know, without me telling you, do you know where the bug started? Do you know the direction that it traveled? Do you know where it was at any given time? No. That's another problem here. So, firstly, they're not functions. Secondly, a lot of times you can't explicitly define them as one variable, and they don't tell where the object is at a given time. I'm going to use time loosely here. Given point, if you want to say, given whatever. We use the word time because parametric equations, I'm going to say this in a little bit, are kind of thought of in terms of time. We'll talk about that. And lastly, I just mentioned this. If you're talking about an object, it's traveling. It's very useful to know where it started, sure, when it was at a given point, where it ended, and the direction that it's taking. Well, if I just give you a line, does it give you a direction? Well, that's a problem. In fact, a lot of times when we do our curves, even if they're functions, we do this. We go, wait, what do you mean? It's going both directions? How can that happen? Where does it start? Where does it stop? I don't know. It's just a series of points. This has the indication that it just goes forever. But it doesn't tell you where it starts, doesn't tell you where it stops, does it? So that's an issue. If we're mapping where an object is going, we need that. We need where it's starting, where it's stopping, and how it's traveling. So this one gives us no direction. So no direction is given. For that reason, we create what are called parametric equations. Parametric equations are the way that you deal with plane curves. So this is not really two different concepts. This is the way that we are going to tackle this. Does that make sense to you? So the way that we are going to go about mapping these plane curves is with parametric equations. So let's talk about it. And I'll give you the idea behind parametric equations. Have I explained everything well enough for you? Do you see the problems I was trying to show you here? They're pretty common sense if you understand what an object is doing when it's moving. You want to know where it starts, where it lands on the board. You want to know where it ends. You want to know when or where it is at any given time. And you want to know the direction that it traveled. So that's why we're going to do these parametric equations. So, parametric equations. Here's what a parametric equation does. It says, you know what, if you're in a plane, you can be described by x's and y's. For sure you can. You can say, at this point you're x and y. That's how planes work. It's why we have a rectangular coordinate system to map any point on a plane. No problem. It's just the way we define it changes a little bit. We say, okay, if we want to describe where x is and where y is, we can actually do it differently than describing y as a function of x or x as a function of y. What we do instead, we say, tell you what, instead of having x as a function of y and y as a function of x, we're going to have x and y as a function of a different variable, an independent variable, time, or t. So that's where we get this parameter. The t is called a parameter, and we say, okay, tell you what, you can actually describe x as a function and y as a function of some other variable. It's still going to give you an x and a y, depending on what you plug in for your time. But in this way, we get away from this, well, if they're not functions of each other, no problem. You can define x as a function of time and y as a function of time. Just say, hey, at any given time, you'll have an x and a y coordinate. Does that make sense to you? So if I said at 1 second, you could plug in 1 and 1. It's going to give you an x and a y. That's going to tell you where that point is and when that point was there. Does that make sense to you? It will in a little bit. I promise it will. So we define the motion of both the motion in both the x and the y directions of some variable t. So I'm going to write that out so we have a good note. So we're going to define motion in both x and y directions as a function of some variable t. And really it's an independent variable. So x and y become dependent variables upon this t. Over a common domain. And we call that domain I. Now here's the words we're going to be using, okay? You want me to go through it one more time, like a 10-second recap?
Yeah.
Okay, so here we go. Our problems with plane curves, problems are real fast. A lot of times they ain't functions. All the time, a plane curve, if you define it as x and y's, it will not tell you where it starts, won't tell you where it stops, will not give you direction. Okie dokie? And a lot of times you can't expressly or explicitly define it in terms of one variable. That makes it difficult for us. So we get around that by saying, tell you what, yeah, every point's still going to have an x and y. Obviously, it's going to be on a plane. It's going to have an x and a y. Let's just describe them different. Let's say that, well, x is now described by a function of time, function of t, whatever t happens to be, and y is described by a function of t, the same variable, but maybe a different way to describe them. So it says, hey, maybe the function of t for x says, in one case, at 1 second you go over 3, and at 1 second you go up 5. Would it give you a point? I'm going to say that again. Maybe at t equals 1, the x is 3 and the y is 5. Would it give you a point? Yeah, it would give you a point 3, 5. It would still describe for you where that point is, but if you do it in terms of t, it doesn't have to be a function. T just goes from wherever you want to start to wherever you want to stop and gives you points. That's all it's doing here, it's giving you points. They can go above each other, they can go around, they can make circles, they can do all sorts of stuff. Does that make sense? And you're going to see that in a little bit. It'll also give you a direction. If we start at t equals 1 and end at t equals 5, where we start at t equals 1, the x, y, notice it's going to give you both an x and a y. That is your initial point, your starting point. Where you end at, let's say 1 to 5 or something. When you end at t equals 5, that is your terminal point, where you're actually stopping. The direction goes from 1 to 5. You can actually follow that curve. And at any t, at any time, you can plug that t in and find out exactly where that object is. And that's a better way of describing the plane curve because it gives us our start, it gives us our stop, and it gives us our direction. That's the idea. Show of hands if it's making a little bit more sense. I promise it will after we do an actual example here. Okay, that t that independent variable that we're basing both our x motion and our y motion on, that's called your parameter. Hence we get a parametric equation. So t is the parameter. And I is simply the interval for your parameter, or the parameter interval. Now, a couple of notes before we get into our example. Typically, and I've already kind of ruined the suspense for you, typically t is thought of as time. Now, don't let this time, it's just an idea, okay? Don't let this time idea make you think that you can't have a negative. T can be negative. It's not like you can't go back in time. It'd be kind of like the rocket launch would be at 0. There's a time, you know how they say t minus 10, die. I would love that part because you feel suspend that, whatever. Okay, I'm a dork. Anyway, we're going to think of it like that. Time can be negative, time can be positive. It's just, it just gives you the idea that this object is moving through a sequence of points, of time points. So, t is usually thought of as time. T is typically thought of as time. And again, I'm going to use that word time kind of loosely here. So let's imagine something. So for some interval, I equals a to b, here's what this means for you. What's t called again? Everybody, what's t called?
Time.
Time, but in more generally? It's called the parameter. That's right. I is the interval for your parameter. So here's what it says. Look at the board here real quick. Time, t. T is going to start where? A. T is going to end where? So we are going to have an initial point, and we're going to have a terminal point, where it starts, initiates its motion, and where it ends or terminates its motion. Does that make sense to you? So for any given closed interval, we're going to have an object starting from an initial point, starts from initial point, and I'm going to leave some space here, I'm going to write something over here. And then ends at a terminal point. I'll just do that. Initial point, because I'm going to need the space here. Initial point to terminal point. Let's talk about the initial point. Now, we just talked about it. Hopefully you guys hung on to it. Tell me, when is the, it's kind of weird to say when, but when's the initial point going to start? At A or B? A. So when t equals A, we are going to get, when t equals A, we're going to get our initial point. Are you all understanding that idea? So t equals A is where we start our motion. Now, here's what I was trying to explain earlier. Look at the board here real fast. If t equals A, check it out. X is a function of t. Y is a function of t. So all you need to do, figure out where this point starts, plug in whatever your t is. If A happens to be like 3, you plug in 3. For both x and y, you get your x coordinate and your y coordinate. Does that make sense? So our initial point would be at, which comes first, x or y? Remember, our points are always x, y. So if we plugged in A, I would get f of A, and I would get g of A. That right there would be my initial point. Notice how f of a is our x-coordinate, g of a is our y-coordinate. That would give us a point. Hey, could you plot x comma y on an y axis? Of course you could. So a parametric equation kind of goes about it in not a more complicated way, but just a different way. It says, tell you what, instead of saying plug in x's, you get y's, it says plug in t's, you get both x's and y's. Make sense? That way you don't have to have a function. Now, your terminal point. Where's your motion going to stop? At t equals b. So if you wanted to find out your terminal point, well, what would you have to do? To where? To t's in... Good. So f of b and f of g of b would give you x and y respectively. Once you understand it, it's not that hard of a concept. It says you can find points x and y by plugging in a number into a function t, a function of t for x, and a function of t for y. It'll still give you points. Now, what happens is that, we talked about this too, if we start at a certain point and we end at a certain point, this will have some sort of an orientation, this trajectory. The object will travel along a definite path. It's not going to travel back and forth like this. It's not going to be randomly as a whole bunch of distinct, unique points. It's going to be, it starts here, it then moves to this point, then this point, then this point along a continuous path until it reaches its end point. Does that make sense to you? So for us right here, we say that this starts from an initial point to a terminal point along some sort of a trajectory with a given orientation. Trajectory has this idea of direction. Okay, are you ready for an example? We've had about 20 minutes of pure theory behind this with no actual example. I hope I've explained it well enough. I think at this point you should have a good idea about what I'm talking about. You should have an idea that what this is going to be is basically you're plugging in a t value for your x and your y independently of each other. And it's going to give you coordinates x, y, which you can graph on a xy system.
Trajectory what?
Trajectory with specific orientation. With specific orientation. And that's another point, in that our curves are going to have a direction to them. So can we start with an example just to give you an idea about what we're going to do? Okay. I want to get through at least like 4 examples because they get very interesting. And I want to make sure that you all understand this before you go today. So, first one. Let's suppose that x equals t squared minus 4 and y equals 2t, and we have -1 is less than or equal to t is less than or equal to 2. Let's see if you guys understood anything about this. Firstly, can you determine that is a parametric equation? Yes, no?
Yes.
What tells you it's parametric?
T.
Is x defined as function of y?
No.
Is y defined as function of x?
No.
Are x and y both defined as a function that they have a variable in common?
Yes.
Like t. That's a parametric equation. Does not have to be t. In the next couple examples, well, after the next couple examples, we're going to use theta. It can be something else besides time, okay? But it has to be the same variable for both these things. That makes it parametric with each other. That's an independent variable of t. Make sense so far? Tell me what the parameter interval is, please. That's all it says. Notice how it's not saying that x goes from somewhere to somewhere. It's not really a domain for x. We can find the domain for x by plugging in t. That's easy. We can find the range of y by plugging in t. That's easy too. But really, our domain idea is more like an interval. It's an interval that time goes for. It says, in our case, if t is time, t starts at -1, it goes to 2, and then it stops. This fly was on the board, this bug was on the board for -1 to 2 seconds or minutes or hours or whatever it was, and it traveled a certain curve. Quick head now if you're okay with that idea. Now, I'm going to do this in two ways. The first way I'm going to do this is show you that you can actually find out your curve by simply plotting points. It's really easy. After that, I'm going to show you that we can make functions sometimes, or we can at least make expressions that we can graph independently. So I'm going to show you both ways. So if you wanted to graph this, where's our t start again? So we probably want to plug in -1 to figure out where this thing starts. So we're going to make up a t table, no pun intended. Okay, we're going to plug in some t values. Now, here's what we're going to get. What we do when we plug in t values, where are we going to plug them in? Yeah, for both of them. And if we plug them in for x and y, we're going to get points out of this. We plug in one number here and here, it gives us 1 point together. Does that make sense? You hopefully, wouldn't want to plug in a t value here and a different t value here and then get the same point, because that would have different times. You'd say, hey, at time equals -1, we're here for x, and at time equals 3, we're here for y. I'm going to put them together. No. It's got to have the same time. So we're going to be getting x, y points, x coordinates and y coordinates. Now, just because it's our first one, I'm going to use several points. Let's use, well, we probably want to know what -1 is. Let's use -1/2. Let's use 0. Let's use 1/2. Let's use 1, and then let's use 2. So in each case, we need to be getting points out of this, not individual numbers, because t goes into 2 different functions. So let's go through it. Help me out with a couple of these, please. If you do, plug in -1, we're going to plug in for both x and y. Plug in -1 for t to get our x coordinate. How much are you going to get? Yeah, hopefully you got -3. Did you get -3? That's our x coordinate. It says, hey, you know what? Plug in -1, you're going to get our x coordinate. Plug in -1, you're going to get, that's our y coordinate. Show of hands if you understand how the points work. If you get that, you get parametric equations, basically, as far as the points go. The t gives you the points, the coordinates for your points independently. It gives you the x coordinate, it gives you the y coordinate. It's still a point, though. So here's what this says. Where does our motion start? What point does our motion, our curve, our object start its motion? What? That's right. Could you graph that on a graph?
Yes.
Okay. When does our object start its motion? At t equals -1. That's the idea. So let's continue. Has anyone plugged in -1/2? Okay, tell you what. How about these 2 rows? You start here. So that row. Far row, do this one. This row, do this one. You guys do this one. You guys do this one. And all of you work together and do this one very fast. Have you guys done this one yet? What is it?
0, 4.
You guys get a tough one.
I know.
This row, what's this one?
3, 2.
What's this one? Okay, how about this one? We'll go this one. You better get this one fast. Geniuses, all of you. These are the hard ones. They're going to be really similar, but these are the hard ones. Did you find this one?
17/4 and 4? Or 1? 17/4 and 1.
I don't think so.
Negative.
Actually, I have it written down. I'm just going to cheat. It's -15/4, I believe.
Yes, it is negative.
And -1, and -15/4, and +1. Is what those points are. Can I get a double check on that just to make sure that...
That's what I got.
Okay, good. I just want to make sure you know how to find them. Do you know how to find them? The math, yeah, you're supposed to know how to plug numbers in on your own, okay? Now, can we graph it?
Yes.
So basically we're just plugging in t for t. Time for here and here. We're getting our x and y coordinates. Let's graph it. Now, let me ask you a question. Let's see if you really do get it. Look up here at the board here with me real fast. Am I gonna wanna plot -1, -1/2, 0, 1/2 on any axis? Do we even have a t-axis?
No.
Don't worry about the t. The t was just to find your x and y. You're graphing in terms of x and y because that is our plane. It's our planar system that we're using here. So we're really just plotting these points. That's all we're doing. So we're going to need -3 then. -1, 2, -3. I don't think we go past this.
-4.
Yeah, -4. Okay, good. So -4. And we're going to have to go up, well, at least 4. Probably 4. Because we almost. Okay, let's plot our points. This should be easy for us. -3, -2 is here. -15, how much is -15 fourths?
3 4.
Yeah, it's almost like -3 3/4. That's exactly -3 3/4. So it's right here, and then -1 is right there. We have -4, 0. We know how to plot that. We're just plotting points. Same thing, but at +1. Okay, we got that. And then we have -3, +2, and then we end at 0, 4. End at 0, 4. Quick head nod if you're okay with this so far. Do you see the curve it's making? Connect the dots. Don't do little lines, okay? Connect the dots with a nice smooth curve. Do we need to go past this way? No, this is where it starts. If our parameter interval is starting at t equals -1, then that's our starting point. Label it. What's that called again? Your initial point. So this is our initial point. Do we have a terminal point?
Yes.
Not toilet paper, okay? Terminal point. You also need to label your direction. So if we have an initial point here and we have a terminal point here, is the object moving upwards or is the object moving down? We'll say this up and down. Is this moving upwards or moving downwards?
Upwards.
It's moving up the curve. So you show that. You show that with an arrow. So this curve, or this object, is moving this way. Just a simple arrow. Quick show of hands, feel okay with this so far? Are you sure? So one way we can define motion of plane curves, notice, is this a function? No. It's a function in terms of x, in terms of y, but it's x equals something in terms of y, but it's not a function in terms of x. You can't say this is y equals something x. So it's easier for us to define this way sometimes, or sometimes it's nicer to do that. It gives us an orientation, direction, starting point, ending point. Now, I'm going to give you another idea. So or. This is what we're going to be working with most of the rest. We don't want to have to always plug in numbers to find points. That's kind of the basis, right? When you learn about graphing, you plug in points, or you plug in numbers to find your points, and you graph those points and make a curve. There's almost always a better way to do this. So let's look at it a different way. Let's start from here. If x equals t squared minus 4 and y equals 2t, maybe we can do some like mathematical razzle-dazzle and combine these things. Let me show you what I'm talking about. Could you solve this for t?
Yes.
If you can solve it for t, more specifically t equals y over 2, you with me?
Mm-hmm.
Could you do a substitution?
Yes.
In this way, sometimes, not all the time, but sometimes we can get an expression that's explicitly in terms of another variable. Sometimes, in this case, we can. Almost all the time, at least for us, about all the time, we can at least make another function out of it. Does that make sense to you? We can at least manipulate it somehow. I'm going to show you that in the next few examples. So, in our case, hey, if x equals t squared minus 4 and t equals y over 2, then what we're going to have is y over 2 squared minus 4, or x equals y squared over 4 minus 4. Okay, I want to show if you guys feel okay with the algebra on that. It's basic algebra. But check it out. Do you guys see that this is a parabola opening to the right that's shifted along the x-axis -4 and has a wider than normal parabola because it's 1/4 there? That's exactly what this thing is. In fact, you could graph this and it's going to be exactly this. Here's the problem though. If I didn't tell you this, if I just had this, it would go forever, right? You'd have to assume t would start at -infinity and go to infinity. It's still going to have a direction. So a lot of times we can make an expression in terms of x and y, like we did here. This is in x and y. But you still have to find the initial point, you still have to find the terminal point, you still have to find the direction. So if you were to do this and I didn't graph the points, so if you say, okay, let's go right to here, here's what you'd do. You'd graph your graph, it would go forever. Does that make sense?
Yes.
From there, what you would do, you would just plug in your initial point, you would just plug in your terminal point. What's going to happen? It's going to be somewhere on this curve, it has to be. So you plug in t equals -1, well you find out you do it from here, you don't do it from here. This is just to give you your curve. So you do this to find your curve. You with me? Are you with me? You plug in your -1, it's going to give you your xy coordinate, it will be somewhere on your curve. You erase the rest of it from where it starts. Or where it doesn't start. You put your terminal point, you erase the rest of it, everything between those 2 points, your initial and your terminal, that's the object in motion. And then, if you know where you start and you know where you stop, you immediately put your direction, and that's what we're looking for. Do you guys feel okay about this example? It's a little simple, but I want to make sure that you guys understand the concept. Show of hands if you do. Feel all right with it? Okay, we're going to nail a couple of them here real fast. I will be going very quickly through the algebra in these, so bear with me. So let's suppose we have x equals square root of t and y equals t. Firstly, is that a parametric equation?
Yes.
Have I given you an interval?
No.
Okay. If I do not give you an interval, you must use what's called the natural domain. You probably have seen that before. So for instance, are there any restrictions on the interval for t here? You plug in anything. Are there any restrictions for the interval on t here?
No.
What can't you plug in?
Can't be negative.
Then right there, you say, okay, tell you what, t must be greater than or equal to 0. We get that from here. Does that make sense? So use the idea of like a natural domain. You say, well, if I don't give you an interval, find your interval. If there's no restrictions, it goes from -infinity to infinity. Quick head nod if you're all right with that one. All right. So maybe write a little note down. I'm not going to write this, but if no interval is given, find the natural domain. For your parameter. Okay, now, if I haven't given you an interval, it's probably not a great idea to just start plugging in some random points. Probably not a great idea. You do know where it starts. It starts at, well, when t equals 0. That's cool, we can find out the initial point real easy. But sometimes it's nice to have a curve to go off of. So for us, we say, all right, well, man, if you look at these two things, if x equals the square root of t and t equals y, x equals the square root of y. Does that make sense to you? In fact, to make this even, right now we actually have the graph. If you want to think about it in terms of x equals square root of y, it's really easy to graph. But you can even make this nicer for some of you. You go, well, okay, square both sides. Y equals x squared. Oh, wait a minute, you can do that? Yeah, you can do that as long as you follow the rules for your parameter. So if we were to graph this, do you know what y equals x squared looks like? I freaking hope that you know what that looks like. Okay, this looks like this. Yes? However, does this represent our parametric equation right now? No, for a few reasons. Firstly, half this graph, it doesn't even exist. Secondly, we don't have our initial point or our terminal point. And thirdly, we don't have our direction. So that's what you start on right now. So start using your interval that you found to find the domain for your x or your y or whatever you have to list out where this thing starts and stops and goes from. So if t equals 0, use that. If t equals 0 and goes positive, look at this. If t equals 0 and goes positive, what's happening to your x? Can x possibly be negative? If x can't be negative, this stuff doesn't exist. Does that make sense to you? Now, use your initial point that you have here. Where's the first place that t starts? If t equals 0, then x equals 0 and y, oh, look at that. X equals 0, y equals 0. What's the point where we start? Is that on our curve that we graphed? That's why we graph our curve first. So right here we have our initial point. Okay, tell me something. Where does the t end?
No.
Does it end?
No.
No. So we don't have a terminal point, but we do have an initial point. If we start here, all this stuff is gone, this doesn't exist. It says that our bug, our object, lands right here at the origin. And then it travels, which way is it traveling? Is it traveling from infinity to here or traveling from 0 to infinity?
0 to infinity.
It is. So we're going to show our direction as going that way. This is the idea. So from t is greater than 0, this implies that x has to be greater than or equal to 0. We get our parametric interval. Well, you could even write it. Where's the parametric interval start? Where's t start? Where's t end? You can even show that. So our initial point starts at 0, 0. We go to infinity, we don't end. Does that one make sense to you?
Yeah.
Are you sure?
Yes.
Okay, let me show you why it's important for you to determine where it starts, where it stops, and the direction. I'll show you right now. This is going to be kind of cool, so bear with me. Did you all understand that problem?
Yes.
So we can find our curve, but that doesn't help us. We have to actually use our t, our parameter, to find out our initial point, and our direction, and what parts of this curve aren't defined. Last example. Okay, here we go. Real fast. First thing, is it a parametric equation? Yes, no?
Yes.
Of course it is. X and y are both defined in some other parameter t. Can you make a curve out of this by combining these two equations?
Yes.
So if x equals t and y equals t squared, then y equals...
X.
Wait a minute. Wait a minute. Wait a minute. That's completely different than that, but I get the same thing. Is that going to be the same curve? Is it going to be the same motion? Is the object going to take the same path? Is it going to be the same curve? So let's think about this. Is weird, right? So what this says is that, can you graph y equals x squared? Then do it. Of course you can. Y equals x squared. Now, here's the interesting part about this. This is where the rubber hits the road as far as parametric equations. You got to use that parameter to determine where it starts, where it stops, and its motion. So check it. In the previous example, we knew that t could not be negative, correct? If t can't be negative, it starts at 0. That's our initial point, and we can't go this way. We can only go that way. Are there any restrictions for the natural domain of t?
No.
Then what's our parametric interval? Okay. Yeah, you're absolutely right. So our time starts at negative infinity. It ends at positive infinity. Am I going to have to erase any part of this curve?
No.
No, because I can plug in. Now, here's what you do to find out where it starts. Just take your negative infinity. It's weird to think about it, but take your negative infinity and plug it in. So if I plug in negative infinity for my t, how much is my x? Yep. So t equals negative infinity implies that x equals negative infinity and y equals... Okay, if I plug in negative infinity, x is negative infinity. Do you guys get that?
Yes.
If I plug in negative infinity here, y is what? Positive infinity. Does that cope well with our graph? Can we start at x equals negative infinity and y equals positive infinity? That's actually exactly where this graph starts. where it would end, if you plugged in positive infinity for t, x would be positive infinity, y would be, oh, positive infinity. It says it starts at negative infinity for x and positive infinity for y, and it ends at positive infinity for x, positive infinity for y. So what direction is it going? Is it going this way or this way? It's not going both ways. It's going, it has a start spot, okay? It starts, remember this, our interval is one direction. The interval starts here, it ends here. So if it starts at negative infinity for t, it starts at x equals negative infinity, y equals positive infinity. It's starting way up here. It's going in this direction. It really technically doesn't end, but the terminal point would be somewhere up there. It does not come back. It goes from this way to this way. That's the way our t flows, our time flows that direction. So time tells us we have that direction. I want to know if I've explained this well enough for you guys to understand it so far. Have I?
Yes.
Okay, very good. The next example, we're going to use something. We're going to use some trigonometry. Can you please brush up on a few of your basic identities, such as the Pythagorean identity for sine and cosine, the double angle formulas like sine of 2x equals 2 sine x cosine x. Brush up on a few of those before your next session, because we're going to use those right off the bat. We're going to go through a few of them. All right, we got our final 3 examples on parametric equations, how to graph them. In the next section, we're going to learn the calculus behind these parametric equations. So, just 3 more. I'm going to go through them, like I said, pretty quickly here. I want to show you some of the things that you can do in order to find the graph of these. So what we're trying to do is get the picture of the graph first, and then find out where the object starts, where the object stops, and what direction it's going on the picture of our graph. Does that make sense to you? We don't want to always have to start plugging in points, because if I'm not giving you the range of your interval, it's going to be really hard to figure out where this thing starts and what the picture looks like without plotting a whole bunch of points. Not sure if you understand what I'm talking about. We want the curve of our object before we find out how it's moving on the object, or on the curve. So, in order to do something like that, sometimes we might have to use some of our trigonometry, some identities, to get a picture of what this graph looks like. In our case, firstly, is that a parametric equation?
Yes.
Do we have an x? Do we have a y? And do we have both of them defined in terms of another variable? Right now, a is not your variable. A is going to be some sort of a constant. The only thing I want you to know is that the constant is the same for both of these equations. Do you see what I'm talking about? So what we get is going to be in terms of a as a constant. We're going to get the same shape no matter what a is. It's just going to be bigger or smaller. I'm going to show you that in a minute. It's going to make perfect sense, okay? What is the parameter then? Is it x? Is it y? Is it theta? What's the parameter? Theta, in this case, is the parameter. It acts like our t. So in our case, theta is the parameter. Now, sometimes it's really hard to solve explicitly for your parameter. For instance, let me have your eyes on the board here real quick. Can I solve that for theta easily?
Yes.
How?
No.
Divide by 8.
Okay, I can divide by 8. That's okay. If I divide by a, I'm going to get cosine theta equals x over 8. You know, remember what we did in the last few examples? If you don't, you're going to have to go check your notes or check the video or something. What we did was we solved for the parameter and did a substitution. Do you remember doing that? That's what we did basically every single time. Is that going to be easy to do here? If I solve for theta, the only thing I can get is cosine inverse of x over a, right? Is that something I want to substitute into this? Probably not, because I'm going to sine of cosine inverse of x. So that's nasty. Okay, so sometimes that's not the best way to go about it, but the idea of get as close as you can to solving for your parameter, such as cosine theta and sine theta equals y over a, that's something we could do. Quick head nod if you're okay with the algebra on that one. So if you can't explicitly solve for your parameter, like we don't want to here, okay? You don't want to do cosine inverse, and you definitely don't want to do sine inverse and try substituting. That's not a good idea. But if you do have like a trigonometric function like these ones are, you have cosine theta, right? you have sine theta. Isolate those pieces. Maybe not theta itself, maybe not the parameter itself, but isolate these pieces, the trig function, cosine theta, sine theta, and then use an identity. For instance, one identity that comes to my mind right now that's really nice that relates sine and cosine very nicely is this one. Do you remember that identity? That's like the one you remember, right? What's that one called? Well, check out why this might be nice. If we can solve for sine theta and cosine theta, then can we substitute these pieces into these pieces? Yeah, in fact, you know what? I'm gonna reverse this. It's going to be the same thing, but just because you'll see it a little bit nicer, I'm going to write this as cosine squared theta plus sine squared theta. Is that the same for you? Okay, let's do the substitution. One's not going to change. Tell me, everybody, what is cosine theta? What? I'm sorry, say that one more time. X over a. So if I have cosine theta equals x over a, cosine squared theta is x over a plus, what's sine squared theta? Yeah, exactly right. If I square both those things, we get x squared over a squared plus y squared over a squared. Oh my gosh, you know what? Some of you might know what the picture of this graph looks like from right here, but you're definitely going to in the next step. Let's get rid of that a squared. What can I do on both sides of my equation to get rid of my a squared? If I multiply on both sides, then I get a squared equals x squared plus y squared. Or if I write that in reverse, so here, x squared plus y squared equals a squared. What the heck? What is that? Do you know what that is? That's a circle. That's exactly what that is. It's a circle. Do you guys see the circle out of that? The form of a circle is x squared plus y squared equals radius squared. Okay, so here's my question. What is my a here? Boom and boom. What is my a? Nope, look up here. What's my a in terms of my circle?
Radius.
A is my radius. So this is really interesting, but it's a way that we can describe a circle without an equation in terms of x and y. This is it. This parametric equation gives you a circle. It just so happens that my radius is this a. So if this was a 2 and a 2, my radius would be a 2. That's right. This is giving my radius right there. Now, if we're to graph this thing, where's the center of this circle? Do you know? You should know. It's at the origin. Remember that with our circles, whatever I would add in here or add in here, whether it's like plus or minus, that's going to shift our center around. So in our case, we're not shifted at all. The center's at 0, 0. Again, how much is the radius?
2.
It's not 2. How much is the radius?
A.
It's a. So whatever my circle looks like, it's going to go out to a. And it's going to go up to, and it's going to go left, negative a, and down. So our circle will look like, by the way, I'm horrible at drawing circles. I'm not good at all, obviously. This is nasty. But it's a horrible circle. But let's pretend I'm good and it's perfect. That's the circle. Yeah, that's really bad too. My bad.
It's okay. So
I gotta make it better.
it's okay, so am I.
Yeah, but you're not being, that's even worse. Okay, whatever, it's my circle. So what this says is, if I can make my trig functions isolated, and I can use an identity, put them together, you can make some sort of a picture of what your graph looks like that's nicer than just looking here. Now, eventually, you're going to get so used to this, you're going to look at that and go, oh yeah, that's a circle. How is it a circle? Your numbers are the same. If your constant is the same and you have cosine and sine, that thing's going to be a circle. And you're going to get used to drawing a parametric equation like that with your radius of a. So if this was a 2 and a 2, I'd have my radius of 2. Show of hands, feel okay with that so far. Now here's the issue. Where does it start? Where does it stop? What direction is it going? Do you know? No, not unless I give you an interval. So I want to be real sure that you're clear on this one. Do you guys get the idea of using identity to put these two things together in a relationship that relates x and y so that you can have some expression in terms of x and y that you can graph? You with me on that one? Nextly, do you understand that without an interval, I don't know where this thing starts, I don't know where it stops, and I don't know the direction that it's going. Do you guys get that? Okay, so we're going to practice a couple intervals. So let's say for the interval 0 to pi. For the interval 0 to pi. Here's my question. If I give you the interval 0 to pi, am I asking you to plug in 0 for x and y or a? Am I asking for that? What is the 0 to pi? What's it relating to? What variable up here? Not time in this case.
The direction.
Theta. It's relating to theta, the parameter. So the interval that you get for a parametric equation is always, relating to the parameter. So in our case it says, hey, you know what? If theta equals 0, could you find me x and could you find me y? If theta equals pi, could you find me x and could you find me y? What are you going to do? Are you going to use this to find x and y? No, go back to your original, the parametric equation. So let's do this together, okay? If theta equals 0, am I going to plug something in for a? No. Okay, so if theta equals 0, how much is cosine of 0? What's 1 times a? So then x would equal what? Very good. X equals a and y. Remember, we use the same theta for both of them. That's how we get our x and that's how we got our y. That's how we started this whole lesson, was you plugging in separately for x and y. They're independent of one another. So if theta now equals, where are we at, 0? If theta equals 0, what's sine of 0? What's 0 times a?
0.
Perfect. Now, what's cool is that that point must be on the picture that you just drew. It's got to be there. So let's look. Do we have a point of a comma 0?
Yes.
Can you plot it on the graph? Is it here?
No.
Is it here? Is it here?
Yes.
That's a0. So this right here, check it out. It's got to make sense for you, okay? Do you understand that our theta is going to start at 0 because that's the parametric interval that we have? So when I plug in theta equals 0, I find my initial point. Does that make sense? So this is initial point. Now, our interval stops at theta equals pi. So whatever I get here, that's going to be my terminal point. Nudge if you understand that idea. So, hey, you know what? Theta goes from here to here in order, in that direction. So it starts at 0, therefore this is my initial point. Stops at pi, therefore if I plug in theta equals pi to my parametric equations up here, I'm going to get my terminal point. So let's do it. If I plug in pi, let's do our x first. How much is cosine of pi? What's negative 1 times a? How much is sine times pi? 0 times a? Is this also on our graph somewhere? It better be, otherwise you did your graph wrong. Okay, it's got to be there. So where's negative a comma 0?
Left.
This one. That now is my terminal point. So here's the 10-second recap before we figure out the direction. Okay, the direction should be very easy. First thing, find some way to relate an equation that contains both x's and y's. That will give you an idea of the picture of this graph. Do that always. Even if it's hard to make the picture, it'll at least give you like symmetry or something so that you can somehow make your picture. Does that make sense? It'll limit the amount of work you have to do as far as plugging in points. It'll really help you. So even if you got to use identities like we did here, get a parameter by itself to do a substitution like we did in the first 3 examples, or get at least a trigonometric expression with your parameter in there, and then use an identity to relate them. Not a big deal. We know the identities. Make your substitutions. You now have an expression in terms of x and y. Hey, that's a circle. Center 0, 0. Your radius is a. Draw your picture. After that, take whatever interval I'm giving you, find the starting point, your initial point. Just plug in the first parameter, evaluate the parameter for whatever your interval starts at. Evaluate your parameter for whatever your interval stops at. That's your initial point. and terminal point respectively. So here's what we know. We start here, we stop here. The next question is, what direction are we going? Are we going this way? We're obviously going one of these ways, correct? We gotta be going either this way or we're going this way. How could you figure that out?
The A.
Say what now?
Up there it says A.
It does, but that just means our radius is not a negative radius, because that'd be really awkward to draw a circle with a negative radius.
Inverted circle somehow. Black hole.
A being greater than 0 means our radius is positive. It's just saying that your circle has a positive radius. Tell you what, we started, do you know what this stands for? Is this x, this is y, or is this theta?
Theta.
And theta is angle, right? Can you give me some angle between 0 and pi? Plug in pi over 2. Just plug in pi over 2. Plug in something between there to give you that relationship. So if I plug in pi over 2, it's going to be easy. Just plug in pi over 2. Plug in pi over 2 here. Everybody, what is cosine of pi over 2?
0.
What's 0 times a?
0.
Okay, well that's right. Oh, sorry, that's wrong. Plug in sine of pi over 2. What's sine of pi over 2?
1.
What's 1 times a?
A.
And there you have it. So, where's our middle point? Okay, let me go back 5 seconds. Do you understand that pi over 2 is right between these things?
Yes.
So that's going to be a point either here or here. It's going to be right between them. Is it the top A or the bottom?
Top.
A? Yeah, it's right there. Does that give you the direction?
Yes.
It says it starts here, it goes through this point, and then it goes through this point. So it's going this direction. I missed. It's going that way. In fact, does it make it down here?
No.
So sometimes our formula in terms of x and y gives us more of the graph than we even need. Here's what this says. This says that this thing is going to make a circle. Are you following me along here? This makes a circle, we've just proven why. It's going to be the whole circle. An interval is going to cut part of this graph. So the interval says if you start at 0 and you end at pi, you don't even have this. That's not even there. It's just starting here, going along the top half of the circle, and ending there. Show of hands if you feel okay with that one. Okay, if you're okay with that, what would this be? If this 0 to pi is a half a circle in this direction, what's 0 to 2 pi?
Entire circle.
Would it still start here?
Yeah.
Would it end here?
No.
Where would it end?
Right at the same spot.
It would be the whole, that would be one full circle, but it would still have the same direction. It'd still be a counterclockwise direction. Don't you have to understand that one? So full circle, same direction. How about this one? Would it still start this now, 0 to 4 pi? Would it still start at this initial point? Would this be the terminal point?
No.
4 pi, not 3 pi.
No.
Would this be the terminal point?
Yes.
Yes.
It would do,
Two revolutions.
yeah, here's pi, 2 pi, 3 pi, 4 pi. Does that make sense? Same direction. So you're going around. It's like, it'd be like you start at 3 o'clock on a clock. Hence the name clock.
O'clock.
Anyway, 3 on the clock. So we'd go backwards. We'd go back in time on a clock. Back in time to 3 o'clock, and then back in time to 3 o'clock again, and do 2 full rotations. This would be 2 circles. But it's in a certain direction. And why that's important is because sometimes direction on how you rotate is important. When you get to calculus 3, you're going to have that idea that you're spinning one way or you're spinning another way. That's kind of a physics idea as well. So whether you're going up an axis or down a different axis. Show of hands if you feel okay with this idea. Okay, good deal. Now, can we extend this idea just a little bit further? Yes, no?
Yes.
You ready for it? I'm going to go quickly through this one as well. And now that we have this idea, this will be a little bit easier. So your ideas. First thing, find some curve that you can sketch. That's what we did first, right? We just did the circle. Then find the initial point. That's easy. Just plug in where your interval starts. Find your terminal point. That's easy too. Plug in where your interval stops. So once I give you an interval, that's easy to do. After that, find the direction. Plug in some midpoints. And then you can find out where that thing goes, whether it's up or down or left or right. And that's the way that we go about doing these. Sketch your graph, initial point, terminal point, direction. That's the idea. Let's try that with this one. Okay, true or false? This is a parametric equation.
True.
Then you got to tell me what the parameter is. Not the interval, the parameter.
Theta.
Theta. What's the parametric interval? So theta is traveling between 0 and pi. True or false? This is a circle.
False.
Why?
Because the radius is not the same.
Ahaha. So if this had been 4 and 4, would that be a circle?
Yes.
If this had been 3 and 3, it'd be a circle. If it's 4 and 3, is it a circle? No. Is it similar to a circle? What do you think this is? It's an ellipse. You're exactly right. This is exactly what this thing is going to look like. Now, we're going to see that when we try to do this same thing, okay? So we don't have A anymore. We have actual numbers, makes things a little bit nicer to graph. So if we're to solve for our parameter, we can't quite get there. We don't want to do cosine inverse or sine inverse. That's crazy, okay? What we do want to do is isolate as much as we can. So cosine theta is x over 4. Sine theta is y over 3. Could I still use the same identity to put those together?
Yes.
Well, I know that sine squared plus cosine squared equals 1. I can do that here. So 1 equals cosine squared theta. I'll put it in this order because I like my x's coming first. Plus sine squared theta. No problem. Do our substitution. That gives us 1 equals x over 4 squared plus y over 3 squared, because I have cosine squared, I have sine squared, so this is sine, hey, sine squared, that's y over 3 squared. Show of hands if you're okay with the algebra on that one. Simplify it. Let's look at what this gives us. We get 1 equals x squared over 16. We get y squared over 9. If you've ever had any intermediate algebra or pre-calculus, which I know you've made it through, you should remember that this is the formula for an ellipse. It's exactly what that is. In fact, when you know that this is radius squared, this is kind of like the idea of radius squared. It's just this is in the x direction, hey, it's under x. This is in the y direction, under y. So what we get out of this, we get an ellipse with, in the x direction, we go 4. Do you see where the 4 is coming from?
Mm-hmm.
And negative 4. In the y direction, we go 3 and negative 3. This is 4 squared, in that direction we go 4 and 4. This is 3 squared, y direction we go 3 and 3. That's where those numbers are coming from. By the way, do you understand why I have this centered at 0, 0?
Yes.
Yes.
Why is it centered at 0, 0?
X and Y don't have any plus or minus.
Very good. So if I have no plus or minus, it's not shifted, it's centered at the origin. Could you make this centered not at the origin?
Yeah.
Sure, if you wanted to, you could do that. You'd have something like 4 cosine theta, and then you'd have like plus 2, minus 1, something like that, where when you solve for cosine theta, you'd have that addition or subtraction on the numerator of your fraction. So if you feel okay with that idea. Now we're going to keep it simple, just have it centered at the origin, makes things kind of nice for us. So let's graph it. By the way, my ellipses always look like Stewie heads or footballs, which are the same thing. So it's going to be awful, but try to make yours better. Oh man.
Oh,
Not even freaking
that looks
close.
like Hey Arnold.
Hey. Looks like an egg.
I told you I'm not very good at this. I wish I was. I had a professor one time who could draw a perfect circle. Not even joking, like
You told
perfect.
us
I did tell you.
Yeah.
He's also a very bad teacher, so.
Wasn't it your physics
I'd rather be a
teacher?
good teacher and not be able to draw circles than a bad teacher who draws perfect circles, because then what use are you anyway?
I bet he's a good art teacher.
I don't care what he is, he's horrible.
What? Did you say he was a physics teacher?
Physics teacher. Man, it was horrible. Anyway, it doesn't matter. So, what I want to know is, have I explained this well enough so to get a bad ellipse out of this parametric equation? You can follow this down?
Yes.
Try to isolate a parameter. If you can't, at least isolate a trigonometric part of that parameter. Use an identity to put them together in terms of x and y so you at least get somewhat what your picture looks like. This gives you exactly what your graph looks like. It's an ellipse. In the x direction it goes 4 and -4. In the y direction it goes 3 and -3. Draw your picture, and now after you've done the picture, this is when you plug in points, not before this. So as soon as you have your picture, you go, okay, let's start plugging in points from our interval. Where does our interval start?
0.
So theta equals 0 should give us something. And where's our interval end? Theta, I'm leaving some space here on purpose, because you're going to see why in a minute. Theta equals 2 pi should give us something. What is theta equals 0 going to give us? Our initial point or our terminal point? Very good. And what's the 2 pi going to give us? That's where our interval goes. It starts here, ends here, goes in a certain direction. Now, where do we plug in this 0 and the 2 pi? Do we do x and y, or do we go back to our original?
Original.
Okay, this is what the parametric equation is all about. It's using theta to find x and y. So plug it in. What's cosine of 0?
1.
So x would equal,
4.
and y would equal, sure, sine of 0 is 0, 0 times 3 is 0, we got 4, 0. Hey, is 4, 0 somewhere on your graph? Hey, where is it at? At 4, 0. That's why we graphed it, so it's got to be there. What point is that again?
Initial.
Okay. Now, let's plug in the terminal. Plug in 2 pi. Everybody, what is cosine of 2 pi, please?
1.
1. 4 times 1? What is sine of 2 pi?
0.
0 times 3?
Sure.
Hey, is 4, 0 on your graph? Wait a minute. We just plotted that. Is that possible? Yeah. It just says that what's happened here is you have an initial point that's also your terminal point. Why? Because we make it how many times around this ellipse? Just one time. Think about how the angle would work here. Theta is an angle, right? It just says you're going 0, you're making it one time around in this case. Well, that's the way we can think about it. It's not exactly that way because we can change the angle, but in our case we do one rotation around that ellipse. We have an initial point that's also our terminal point. Does that make sense? Now, to prove that you only go one time around this and not 2 times or 3 times or something crazy, if our angle is a little different, what you have to do is plug in some points between there. So I'd plug in points like, well, give me an easy one to plug in between 0 and 2 pi. Pi'd be great. Give me another one.
2 pi over 2.
Pi over 2. And plug in those values. And that way you determine that you don't go around more than one time. You don't just want to make that assumption, okay? So because right here, if you did that, if you plugged in 0 and 4 pi, you're still going to get initial and terminal, but you're not going to know it goes around twice unless you plug in those middle values. Make sense? So we're going to plug in stuff like theta equals pi. We're going to plug in stuff like theta equals pi over 2 and theta equals 3 pi over 2. And we're going to get a variety of points. But notice what I'm not doing. I'm not plugging in my points first. I'm not plugging in my thetas first. I'm getting my picture first. That's important. You want to figure out what it looks like. That way you can put where your starting point is on the graph, and you can determine where all your other directions go, or well, not your directions, your direction is, and what your other points are already on the graph for you. So if we plug in pi, what we're going to get is -4, 0. That's here. If we plug in pi over 2, we're going to get 0, and we're going to get 3. Here we're going to get 0, and we're going to get -3. And what that shows you is that if you go in order, it says we start here at 4, 0, then we go to 0, 3, then we go to -4, 0, then we go to 0, -3, and we finally end up at 4, 0. So we're going in this direction. That would make one full rotation. So what you do, sketch it, label your initial point. It's got to be on your graph, otherwise you've done this wrong. Label your terminal point. It's got to be on your graph, otherwise you did it wrong. And then label your middle point somewhere. That gives you your direction. Show of hands if I explained this well enough for you. Okay, we're going to do one more. Are there any questions before we keep on going? You sure you're good with it? It's not that bad, right? As long as you know to relate in some sort of a formula with an identity. If you don't have this part, then this is why I asked you to look at those trig identities before you start this lesson. So if you don't have that part, you know, oh man, what am I supposed to do here? Just plug in a whole bunch of points? It's going to take you forever. If you don't know what this thing looks like, it's going to take you forever to actually figure out what's going on. Not forever, but it's going to take you a lot of plugging in points, okay? Man, what am I supposed to plug in? I don't know. Well, it's going to take you a bit. If you know what the picture looks like, okay, shoot, that's a circle. Starts here, ends here, it's got to go either this way or this way, plug in one point, you're done. All right, same thing with okay, last one. This is a little bit more advanced, so I want to walk you through one that is a little more difficult so you get used to it. Okay, here we go. So,
Are we always going to be given an interval?
if you're not, then you assume it goes from negative infinity to infinity. All right? With a trigonometric function like this, because they are cyclical, circles, right, or ellipses, or what this is not going to be a circle, well, I'll get to that in a minute, it's going to oftentimes repeat. And so generally you're going to be given an interval for that, because you got to have a starting point somewhere, right? It's got to land on the paper. The object has to land on the paper or on the plane and then go around it. So no, I think I gave you a couple in the last part of this lesson, like last time, where I didn't give you an interval, like the square root of t, in which you said, well, the natural domain for that parametric, for that parameter is 0 and positive. Well, that gives it to you. But then I gave you another one where it was t and then t squared, in which you don't have one. You have to assume that your t starts at negative infinity, plug that in, figure out where your graph starts. That's why you graph them first. Because what if I didn't give you an interval? You literally have nothing to plug in, right? How are you going to do that? So you got to figure out what the graph looks like first before you start plugging in parameters.
You ran on the test, can't do it.
Can't do it. Done. Yeah, don't do that. Okay. All right, now let's walk through this one. I'm going to try to go a little slower, but we also need to get this done in this lesson. So if we have x equals sine t and y equals sine 2t, start from the beginning. What type of an equation is this? Parametric equations right here. What is the parameter in this case?
T.
What's the parametric interval? Very good. Okay, so we know that we're going to have a starting point at t equals 0, ending point at t equals 2 pi. True, false, this is for sure a circle.
False.
It doesn't look at all like what we've had. Before, what we had was something cosine and something sine, and we had theta and theta, or t and t. You with me? The parameter doesn't matter really what it is. In our case, t is going to be like an angular relationship here. So it's not going to be a circle. We're going to have to do some work to figure out what this is. Now, the idea is you want to try to isolate the parameter, or at least, if you're given trigonometric functions, isolate a trig function with the parameter in it, which is also isolated. So for instance, this one, can I isolate the t?
Yes.
Do I want to isolate the t with a sine inverse?
No.
Don't use sine inverse. Can I isolate the t? No. Can I isolate the sine t?
Yes.
Done. That's nice. Can I isolate the t? No. You don't want to use sine inverses. Can I isolate the sine t? That's what I'm going to work on, okay? I don't want to isolate sine 2t. I want sine t in there somewhere. So if I start with like y equals sine 2t, so here's the start of our example. If y equals sine 2t, that's really not what I'm looking for. And the reason why I'm not looking for it is because I'm going to try to do this again. I'm going to try to do cosine squared theta, or in this case cosine squared t, and sine squared t. If I have 2t, that's not going to fly very well. Make sense? Use an identity. Do you know an identity that gets rid of that 2?
Double angle.
Yeah.
Sine of the cosine of
Yeah, so maybe we got to use that. You guys okay with this so far? You sure? Now, why you try to isolate those trig functions is because a lot of times when you're doing this, if you've isolated the trig function, it's going to give you an expression in terms of the other variable. Check this out. Do we know how much sine of t is? Yes. This right here is x. So y equals 2x cosine t. Now, can I isolate a parameter, even if it has a trig function around it, and make it in terms of x and y alone?
Yeah.
Are you listening to what I'm saying? Can I isolate the trig function here, even if it has, isolate the parameter, even if it has a trig function around it, and make it in terms of x and y alone? How would I do that? Isolate it. Say what? Divide by 2x, okay. So I get y over 2x equals cosine t. I know that some of this is like, wow, why are you doing this? The idea behind this is you want to get a parameter isolated so that you can make a substitution, or if you can't get a parameter isolated, like in this case, if you can't do that, at least find something you can use in an identity, a nice identity that will allow you to put those parameters together. Okay, so for us, we go, hey, parameter isolated? Not really, but with the trig function, yeah, it's good. This equals x. Why we get that is so that you can make a substitution right here for an identity that's useful for you, okay? This one, not good at all. We can't put this in an identity and make sense out of it where we can make both of these things together. There's no identity that allows you to put sine t and sine 2t together besides, well, this one. Right? That's it. So what we're going to have to do is make this identity here. Well, if you do, you immediately can plug in x for sine t. That's nice. This is x. Sine t is x, as given by a definition of our parameter. So that's cool. Now, as soon as you make this into an x, can you solve it for the other one? And as soon as you do that, as soon as you solve it, now we have sine t equals x. We have cosine t equals something in x and y. Now let's use that identity. So if we have 1 equals cosine squared t plus sine squared t. Stick with me here, folks. Do I have an expression for cosine t?
Y over 2x.
Okay, so if cosine t is y over 2x, then cosine squared t is y over 2x squared. Plus, do I have an expression for sine t?
Yes.
That was the easy one. That was given to us like that. So if sine t is x, then sine squared t is x squared. Show of hands feel okay with it so far? All right, let's continue working then. Let's start simplifying. So this is 1 equals y squared over 4x squared plus x squared. So far so good? This is nasty. Do you know how, now, this was cool over here, right? The graph was very easy to see. This was simply an ellipse. Is the graph easy to see here? Okay, so simplify it a little bit if you can. Work with this then. Multiply everything by 4x squared because I don't like denominators. Okay? So 4x squared equals y squared plus 4x to the 4th. Can you follow me on the algebra?
Yeah.
Maybe you get everything to one side. We like functions looking like that. So subtract this. I get 0 equals 4x to the 4th minus 4x squared plus y squared. Can you verify on the algebra on that one?
Yeah.
Subtracting this plus that. Now, oh man. So if hands feel okay with the algebra, the idea behind it. So again, the idea, isolate a parameter if you can. If you can't, at least isolate the function around your parameter, like sine. Or use an identity so that you can isolate cosine t. Isolate something. You might have to use a substitution just to isolate that. You with me on that one? You sure? Okay. Well, then use an identity and put them together. So if I have cosine t and sine t, I know I can use this identity, Pythagorean identity. Work it out. Make them in terms of x and y. The reason why we do this is not necessarily, we like getting the picture, right? That's nice. That's awesome. But even if we can't get the picture, for instance, do you know what this graph looks like? Is this a circle?
No.
An ellipse?
No.
Like anything you've ever seen before, probably, right? No, it doesn't. But at least it will give you some hints as to what this picture will do so that you can plug in less points, the least amount of points possible. For instance, if I look at this, do you see how my x's are both being squared? What that tells you is that in terms of x, this is an even function. That means it's going to be symmetrical about the, not the x-axis,
Y-axis.
the y-axis. Remember even functions, how they do that? Basically it says this, if I plug in negatives, listen to why, because I know some of you know the term even function, but you really don't understand what it means. What it means is that when you plug in positives and when you plug in negatives, you get the same thing out. Because you're taking to the second power and to the fourth power. That means if I plug in 2 or negative 2, I get the same output. Does that make sense? That means it's symmetrical about the y-axis. So these things right here, this says it's even in terms of x, that means symmetrical about the y-axis. What's that one tell you? If y is being squared. About the x-axis, that's right. Because when I plug in y equals 1 or y equals negative 1, I would get the same x out. Okay, well that means it's symmetrical about the x-axis. So here's the point I'm trying to make. Even though this doesn't give you an exact picture of what this graph is going to look like, it tells you that it's symmetrical about the x and it's symmetrical about the y. Basically, you just need to plot the points in quadrant 1, and then you get quadrant 2 for free. Then you get quadrant 3 for free, and by the transit property, you get quadrant 4 for free. Going backwards for you guys. So you'd get, if you do quadrant 1, you get quadrant 2 for free and quadrant 4 for free. Therefore, you can get 3 either way you go. So if it's reflected across the y-axis and the x-axis, or the x-axis then the y-axis, it's hard to move my hand that way, you gotta excuse me. Somehow you're gonna get this one, and that one. Does that make sense? Okay. That limits the amount of work you have to do. You don't have to plug in every single value from 0 to 2 pi. That'd take you a long time. So by doing this, well, we figure out that we plot quadrant 1, and then we're going to get quadrant 2, 4, and 3, and the direction has to work with this. So if we do quadrant 1 and the direction, it's going to give the rest of it up for basically free. So it's not useless. This gives you a lot of useful information. So what we're going to do, since we have this goes through all 4 quadrants, let's plot just the first quadrant. So 0 to pi would give us the first 2 quadrants. 0 to pi over 2 would give us just the first quadrant. Does that make sense? So we're going to do a whole bunch of points, but they're all going to be in quadrant 1. So let's start here. So what we're going to do is we're going to find some points between 0 and pi over 2 and use symmetry to give us the rest of them. What are some good values to plug in for t? I know 0 is one of them, obviously. And what's another good one we're going to plug in?
Pi over 2.
Oh yeah, pi over 2. Yes, pi over 2. We're going to need that.
Pi over 6.
Pi over 6 is a good one.
Pi over 4.
Yeah, pi over 4 is a good one.
Pi over 3.
Pi over 3 is a good one. Now put them in order.
Pi over 6.
What's in the middle?
Pi over 4.
What's in here?
Pi over 6.
Good. Pi over 6 is here. And pi over 3 is here. Is that okay? Yeah, it's helpful to know a unit circle. plug in these t's. Are we going to plug it in here?
No.
Here? Here?
Yes.
And there?
Yes.
So don't forget that when you plug it in here, how does that work? What should you do?
Multiply by 2.
Before you do the sign or after you do the sign?
Before we start.
Okay, so that's important that you know that. So when we plug these things in, I'll do it with you because we got to kind of go fast, but I'm sure you can do it on your own. Let's take 0. So we're going to plug in our t because it's a parametric equation to the parameter where we get our x and our y coordinates from. So what's sine of 0? So therefore x here is 0. What's 2 times 0?
0.
Sine of 0?
0.
So we start at 0, 0. I'm going to do this as we go. Our first point is what?
0, 0.
What do we call that? I know it's the origin, but in
The
terms of
initial point.
that's very good, initial point. And the origin, you're both right, my bad. I should have been more specific. Initial point. Very good. Now, well, how about pi over 6? Let's do sine of pi over 6. What is it?
1/2.
And remember what you do here. You do 2 times pi over 6. That's pi over 3. What's sine of pi over 3? Okay, how about pi over 4? Let's do sine of pi over 4. What is it?
2.
How about this one? What's 2 times pi over 4?
5.
2 times pi over 4 is?
2.
What's sine of pi over 2?
1.
How about pi over 3? What's sine of pi over 3?
3.
We already kind of did it. That gives us our x coordinate. Now, remember we multiply by 2. So 2 times pi over 3 is 2 pi over 3. What's sine of 2 pi over 3?
1/2. 3 is here.
You know? Look it up. Look up yours. I'll do the hard one for you, okay? I'll do this one, and you guys take care of that.
Be louder, Jessica.
So sine of pi over 2 is 1. And then if I do, well, 2 times pi over 2 is pi. Sine of pi is 0. I already did it for you. Oops. 0. Figure that one out yet?
Negative square root of 3 over 2.
Is that positive?
It's positive.
Positive?
All students. So sine is positive for the first 0 to pi. So let's see. Sine counts up. Sine counts up. So sine goes 0 over 2, then 1 over 2. Actually, square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, then square root of 3 over 2. So where is 2 pi over 3? 2 pi's over 3 would be, this would be pi over 3, and then this would be 2 pi over 3. So it's root 3 over 2. Double check that for me, make sure I'm not wrong too, am I right? That's right. Let's plot those points, all right? Can you plot those points? Are they all numbers?
Yes.
All right, we already had the initial one, 0, 0. What's the terminal point? For this, this like sub-interval that we have, what's the terminal point?
1.
So I know I'm going to make this kind of extended, that way we have a good graph here. So here's 1, let's make sure we get 1. And then that's about right, 1. And 1. Okay, here's what we know. We know it starts here, and it's going to end for our little sub-interval at 1, 0. Quick head nod if you're okay with that so far. All right? Is it just going to go,
No.
darn it, that'd be cool, right? It just goes like this. No, it doesn't do that. It goes along this course. So we have 0, 0. It's going to end at 1, 0 for this little sub-interval. The next point it's going to go to after 0, 0 is
1/2.
So 1/2 is right in the middle. Root 3 over 2. How much is root 3 over 2? Is it more than 1 or less than 1? It's less than 1. Right, let's just, we're going to approximate right about there. Now, when I plug in root 2 over 2, root 2 over 2, when I plug in pi over 4, I get root 2 over 2 and 1. Where's root 2 over 2 in relation to 1/2? Is it more than 1/2 or less than 1/2? It's more than 1/2, but it's less than 1. So if I plug in x equals root 2 over 2 and 1, I'm going to get something right here. How about root 3 over 2, root 3 over 2? Where's root 3 over 2 in relation to root 2 over 2? Is it, so here's root 2 over 2. Is it to the right or to the left? To the right, but not very much. Not a whole bunch. It's right about here. And then, do we go up to 1 or just under 1? Actually, the same exact level as that was. Here's how our graph looks. Show of hands if you feel okay with those points. There's points on the graph. Use your calculator if you want to approximate with decimals. So this goes up to this point, and then down to 1. I know I'm not a great artist, but do you guys see the way that this graph should look? Yes, no? What direction is it going? Is it going this way or the reverse way? Way number 1 or way number 2? Way number 1. Now, this is what is nice. Because we've already determined this is symmetric about the x and symmetric about the y, where is it going to jump to now? Is it going to jump to quadrant number 2 or quadrant number 3 or quadrant number 4? It's going this way. Can your bug do this? I mean, I know it literally can, but can it stay on the plane and jump from here to here? Not unless it has like a wormhole. That's right. You Star Trek dorks. Star Wars is where it's at. Fools. Just joking. I like Star Trek too. So it can't go from here to here. That doesn't make sense. It must continue along its path. So here's how it looks. It's symmetric. So that means it goes like this, but then it continues down here. Let's see. Right about there. Continues down here like this, and does that. Do you see it? And then it's going to continue, well, let's see. This goes up or this goes down? The direction goes up or down. It must follow the path. Follow the path, my Padawan learners. Starts here, goes like this, hits this one. Hey, we hit our initial point. Are we done? No, because we also know it's symmetric about this and this. So from here, is it going to go down this way?
No.
It's going to go up. And you might want to plug in a couple points to do that, but it can't do this. It's got to go this way. So right up there.
Second infinity.
It's going to continue this way, going to continue this way. By the way, could you plug in some points to double check this? You could always do that, but at least now you have a picture of what this thing looks like. It's nice. Lastly, it's also symmetric about that. We go this way, and now we wrap it up. So what's going to happen? At 0, we're here. If I plug in pi over 2, I'm going to be here. If I plug in pi, I'm going to be back to here. Plug in 3 pi over 2, I'm going to be here. Plug in 2 pi, I'm going to be back to my origin. So that is also my terminal point. But it does one full lap around that track. It's like a race car driver. And then turns and is going, then back to start, and then it goes around the other corner. You ever seen those ones where they have like a figure 8 racing? That's crazy stuff. That's what this is. Show of hands if that one made sense for you. Cool? Can you do it? I think you can.
With some time?